We are in section 7.3, Trigonometric Substitution. We have done substitution up to this point in effort to transform a complicated integral into a less complicated integral. In this section, we will be doing the same thing, although it may temporarily look more complicated before it gets less complicated. Recall the Pythagorean formulas allowed us to rewrite each side of a right triangle in terms of other two sides. So in the table below, we are given three different cases here depending on which expression we are given. A is just a numerical value. For the most part, it could be a variable, but x is usually typically our variable. So we would have the square root of a squared minus x squared, the square root of a squared plus x squared, and the square root of x squared minus a squared. And depending on these three cases, which are all sketched next to the box, we would have a different substitution. So for the first case, the square root of a squared minus x squared, we would use a trig identity of 1 minus sine squared theta equals cosine squared theta, and the substitution that we would be using is x equals a sine of theta. Likewise, for the second case, we would use x equals a tangent of theta. Third case, x is equal to a secant of theta. Also note that theta is given in between different values, so we're restricted to certain quadrants. So the first example that we have says evaluate the integral of x squared over the square root of 9 minus x squared dx. First thing I notice is that I have a numerical value squared, which would be 3 minus x squared, and it's inside that square root. And so this would be the first case that we have written in the box right above. And so I'm going to go ahead and sketch the triangle. A lot of students find it helpful and more visual to see it. And with sketching this, I know that A is equal to 3, and x would be over here. And then I'd have the square root of 3 squared minus x squared, or 9 minus x squared, but I'll write as 3 squared minus x squared. So from our diagram given here, we can see that sine of theta is equal to x over 3. And that means that x is equal to 3 sine of theta. So we're going to let x equal 3 sine of theta, which you can see is what is up in our box, what we should be using for our substitution. And then dx would equal 3 cosine theta d theta. So our expression here in our integral is the square root of 9 minus x squared. And so I'm going to go ahead and say that since we know that x is 3 sine theta, I'm going to go ahead and substitute that in. And so this is going to be 9 minus 3 sine theta squared. And so from here we know that we have 9 minus 9 sine squared theta. I go ahead and pull that 9 out. So I have 9 times 1 minus sine squared theta. And we know that we would then have the square root of 9 times cosine squared theta by the Pythagorean identity. And then from there we know that's going to be equal to 3 cosine of theta. We can then use this to rewrite our original integral. And so we had the integral of x squared over the square root of 9 minus x squared dx. And so we have now the integral of x is 3 sine theta squared over, and we just rewrote the square root of 9 minus x squared as 3 cosine theta. And then we have dx, and we have dx up above, and dx was 3 cosine theta d theta. So a few things to note here. We went from having the x variable to now being in terms of theta, And so if we had a definite integral, we need to take that into consideration. From here, I'm going to go ahead and simplify this a little bit more. Cosines of thetas and the 3's would reduce down. And I would end up with the integral of 9, I'll put that out in front, sine squared theta d theta. And we are unable to integrate sine squared theta. However, we can use a power reducing formula and rewrite this as 9 times the integral of 1/2 times 1 minus cosine 2 theta d theta. So we have 9 over 2. The integral of 1 would just be theta minus 1/2 sine of 2 theta. And since this is an indefinite integral, we will go ahead and add our plus c. So from here, we know that we have 9 over 2 theta. So if I distribute this, minus 9 over 4. And there's a little bit of an issue here because I defined x in terms of theta, and right now I have a double angle. I have sine of 2 theta. So I'm going to convert this back into just regular theta, not double angles. And so I have 2 sine theta cosine theta, and then obviously your plus c again. And then from here, we need to go ahead and rewrite this in terms of x's. And so in order to do that, I would have to solve for theta. And since right now we have x equals 3 sine theta from up above, so we had x equals 3 sine theta, so if you divide both sides by 3, we have x over 3 equals sine of theta. And then if you did the inverse of sine, we would have theta is equal to sine inverse of x over 3. So I will need this in order to rewrite my answer in terms of x's. I also want to note that we still have sine of theta and cosine of theta. In order to rewrite those in terms of x's, I will use the triangle that we drew up above. So from here, I have 9 over 2 theta, and instead of theta, I'm going to write this as sine inverse of x over 3 minus 9 over 4 times 2, so this is now going to become 9 over 2, if you reduce those down. And sine of theta, we've defined that even over here without looking at our triangle as x over 3. And then cosine of theta, if you look up at your triangle, your cosine is going to be your adjacent side, which is the square root of 3 squared minus x squared, over your hypotenuse, which is going to be 3. And so that would be the square root of 9 minus x squared over 3, and then our plus c. So cleaning this up just a little bit, we arrive at 9 over 2 sine inverse of x over 3 minus, simplifying this, we would be able to reduce down a few things, and we have x times the square root of 9 minus x squared over 2 plus our constant c. And so I would encourage you to sketch that triangle to kind of see the sides and the relationships between those sides and the angle theta. So the next one that we have, I have evaluate the integral of dx over x squared times the square root of x squared minus 16. So I notice that I have an x squared minus a squared, or 4 squared for this case. So that's the third case on the table of trigonometric substitutions. So the first thing that I'm going to do is sketch our triangle and put theta on our right triangle here. And it's x squared minus 16. And so since I have an x first, that would be my hypotenuse, and then I have my adjacent side my opposite is going to be x squared minus, I'll leave it as 4 squared. So that means we know that cosine of theta is equal to 4 over x, or you can think of it as being secant of theta is equal to x over 4 by taking the reciprocal of both sides. And then solving for x, we know that x is equal to 4 secant of theta. So from the table up above, or kind of deriving it yourself, you get let x equal 4 secant of theta. So then our derivative dx is going to be 4 secant theta tangent theta d theta. And the radical part that we are dealing with here is going to be the x squared minus 16. And we defined x as 4 secant of theta. So 4 secant of theta squared minus 16. And this would be 16 minus secant squared theta minus 16. So I will factor out that 16 here. And I have 16 times secant squared theta minus 1. And from the Pythagorean identities, we know that secant squared theta minus 1 is tangent squared theta. So we have 16 times tangent squared theta. And taking the square root of both of these, we would arrive at 4 tangent of theta. So our original integral, which is dx over x squared times the square root of x squared minus 16, can be rewritten as the integral. In the numerator we have dx, which we found as 4 secant theta tangent theta d theta. We have x, which is 4 secant theta, and we have that squared. And then we have that the square root of x squared minus 16 from our substitution is just going to be 4 tangent of theta. So from here we can simplify this. Our tangents would reduce down, 4 would reduce down, one of the secants would reduce out, and we're going to end up with the 4 is still squared here, so we would have the integral of 1 over 16 secant theta d theta, which can be rewritten as 1 over 16, putting that in front. 1 over secant of theta is just cosine. So cosine of theta d theta. If you integrate this, you get 1 over 16 sine of theta plus c, since it is an indefinite integral. And sine of theta, if you look back at your triangle up above that relates x's to theta, or angle, we know that we have 1 over 16 times sine, which is our opposite side over our hypotenuse. The opposite is going to be our x squared minus 4 squared, or 16, over x plus c. And you can leave it like this, or write it maybe just a little bit cleaner and say the square root of x squared minus 16 over 16x plus c would be our final answer. So we have a definite integral in the next one. I'm going to go ahead and circle that, and we'll look at that one together in class. The example at the top of the next page says evaluate the integral from 0 to 2/3 of the square root of 4 minus 9x squared dx. The first thing I'm going to do is draw my right triangle so I can see how to use trig substitution for this problem. So I'm going to put theta on, and it's 4 minus 9x squared. So 4 is going to be my hypotenuse, which again, remember, needs to be squared, a squared, so this would be 2. And then the opposite side is going to be 9x squared, but again, that needs to be squared, so that would be 3x. And then the other side would be that radical, which is going to be 2 squared, or 4 minus 3x quantity squared, or 9x squared. So we can see that sine of theta equals 3x over 2. Or you can say that sine of theta, and multiplying both sides by 2/3, we would have x equals 2/3 sine theta. So that's what we're going to let x equal. And then our dx is going to be, our derivative will be 2/3 cosine theta d theta. So from here, I'm going to go ahead and look at that radical that we have. And so we have 4 minus 9x squared. And we know that x, as defined up above, x is equal to 2/3 sine theta. So I'm going to go ahead and put that in. So the square root of 4 minus 9 times 2/3 sine theta. And then it's squared. And so then we're going to have the square root of, and it's 4 minus 9, and this is then going to be 4 over 9 sine squared theta. So the 9's are going to reduce down. I can factor out a 4, and then I'm left over with 1 minus sine squared theta, which again, by Pythagorean identity, is just cosine squared theta. And then taking the square root, we end up with 2 cosine theta. So now I'm going to use trig substitution. I'm going to go ahead and rewrite my problem, which is from 0 to 2/3, the square root of 4 minus 9x squared dx. And from here, I know that 4 minus 9x squared, the square root of it, is equal to 2 cosine theta. So I'm going to have the integral of 2 cosine theta times, and then for dx, we have that over here, that is 2/3 cosine theta d theta. And also note that the variable has changed. We are now integrating with respect to theta and not x. So since I'm dealing with a definite integral, I do need to change my lower and upper bounds. So we defined x as 2/3 sine theta, and I don't have much room over there to do my work, so I'm going to go ahead and write it again over here. So x is equal to 2/3 sine theta. And so I'm going to go ahead and show my work for my lower and my upper bounds. So the lower bound was equal to 0, and that is my x value. So 0 equals 2/3 sine theta, and I'm solving this for theta. And then my upper was 2/3, so 2/3 equals 2/3 sine theta. So solving this first one, multiplying by 3 over 2, I get 0 equals sine theta, or just theta is equal to 0. So my lower limit of integration is still going to be a 0. And then for this one, multiplying both sides by 3 over 2, I get 1 is equal to sine theta. And sine theta is equal to 1 when theta is equal to pi over 2. And so from here, my integral, which goes from 0 to pi over 2, I'm going to go ahead and pull that constant, which is 2 times 2/3, or 4/3 out in front. And I'm going to have cosine squared theta d theta. So to integrate cosine squared theta, we use that power reducing formula. So I have 4/3, the integral from 0 to pi over 2. And cosine squared theta is the same thing as 1/2 times 1 plus cosine 2 theta d theta. And from here, we can pull out the 1/2. That's going to now become 2/3 out in front. And I'm able to integrate this with respect to theta. So we'd have theta plus 1/2 sine 2 theta. And we're going to evaluate this from theta equals 0 to pi over 2. So substituting in pi over 2 first, we have 2/3 times pi over 2 plus 1/2 sine 2 times pi over 2 minus 2/3 times, then I have 0 plus, and then substituting in 0, sine of 0 is just 0. And from here, I'm going to have 2/3 times pi over 2 plus, then 1/2 times sine, our 2's reduced to just sine of pi, which is just 0. And so our answer is going to be pi over 3. The next example says, evaluate the integral of x over the square root of 1 plus x squared. And so I would think of using trig substitution for this problem. However, if you go back and look at your table with the different options we have, none of those work. And actually, this is going to be set up just by using u substitution. So we would have to say, let u equal 1 plus x squared. So du would equal 2x dx. And so my integral is now going to become the integral of, and it's 1/2 times 1 over the square root of u du. And I'll put the 1/2 out in front and then rewrite this as u to the negative 1/2 du. And then integrating this, I'd have 1/2 times u to the positive 1/2 times 2 over 1 plus c, since it is an indefinite integral. And from here we get the square root of u plus c. Back subbing in what u is, square root of 1 plus x squared plus c. And this would be my final answer. So a few things to note. When dealing with integrands that have radicals and an x squared or a variable squared, think about trig substitution, but also don't forget that you learned how to deal with these types of problems. Certain cases where u substitution will work. This would not work with trig substitution. You would have realized that it's not on the table and you would have been stuck. And also, again, make sure you always go through and try u substitution. Think about that first, and then integration by parts, and then all these other things that we have. So the next example, I'm going to go ahead and circle, work on that one together in class. And at the top of the next page, it says, evaluate the integral of dx over the square root of x squared minus 6x plus 13. So first of all, this doesn't look like what we've dealt with before. It's not written in the same form. It would be nice if I could factor this nicely, but it doesn't. So what we are going to do is we are going to complete the square, and that way I can rewrite this the correct way. In order to do that, I need to use the idea of b over 2 squared. And b is negative 6 in this problem, over 2 squared, which would be negative 3 squared, which is just positive 9. So positive 9 is what I'm going to add and subtract in order to do this, completing this square. This is an Algebra 2 idea, and hopefully it's something that you remember. If not, definitely reach out and ask. So this is going to be the integral of dx over the square root of, and I have x squared minus 6x, and I'm going to add 9 and subtract 9. So plus 9, and then I also have a plus 13, and I'm going to subtract 9. So from here we have the square root of dx over, and this is going to be the square root of, and x squared minus 6x plus 9 is going to be just x minus 3 squared. And then 13 minus 9 is going to be plus 4. So from here, I notice that has that form that would work for trig substitution. I'm going to go ahead and draw my right triangle. So putting theta on, I see that my two sides are going to be x minus 3 and 2. So x minus 3 and 2. And then the hypotenuse would be adding those two together. So x minus 3 squared plus 4. And so rewriting this, I know that tangent of theta is equal to x minus 3 over 2, which means that x minus 3 would equal to 2 tangent theta. So I'm going to let x minus 3 equal 2 tangent of theta. I know it's written a little bit different. Taking the derivative of both sides, I get dx, since the derivative of negative 3 would just be 0. And we get 2 secant squared theta d theta. Next, I'm going to look at our radical, which was originally x squared minus 6x plus 13, which we used completing the square method and rewrote this as x minus 3 squared plus 4. And I know that x minus 3 is defined as 2 tangent theta. So I have the square root of 2 tangent theta squared plus 4, which is going to be the square root of 4 tangent squared theta plus 4. I can factor out of 4, and I have tangent squared theta plus 1. And tangent squared theta plus 1 is secant squared theta. So this is going to be 4 secant squared theta, which simplifies to 2 secant theta. So now I'm going to look at my integral that we have. And we have the integral of dx over, and it's the square root of x squared minus 6x plus 13. So our original integral would equal, and we know that dx is equal to 2 secant squared theta, and also the square root of x squared minus 6x plus 13 is equal to 2 secant theta. So substituting both of those in, we get 2 secant squared theta d theta over, and then the square root of x squared minus 6x plus 13 is going to be 2 secant theta. And we get the integral of secant theta d theta, which we can integrate, and we have ln of the absolute value of secant of theta plus tangent of theta plus c. Looking at the triangle on the right, we have the natural log of the absolute value of secant is going to be the square root of x minus 3 squared plus 4 over 2 plus tangent of theta is going to be x minus 3 over 2, and then we have plus c. So another way to express your answer, instead of having the square root of x minus 3 squared plus 4, which is what we had used completing the square to rewrite it, you can write that as the original square root that we had, which is the square root of x squared minus 6x plus 13.